The Hong Kong Polytechnic University, PolyU, leverages its world-class academic and research excellence to develop innovative solutions for a more sustainable tomorrow. In July 2022, the PolyU Academy for Interdisciplinary Research PAIR was established as the university's central research platform, dedicated to providing world-leading, interdisciplinary solutions to address significant societal challenges. PAIR is composed of multiple constituent research institutes and research centers. Each research unit focuses on a particular research area and is joined by researchers from various PolyU faculties, schools, and departments. PAIR research areas include advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. PAIR researchers develop new materials, systems, technologies, and techniques that support industrial modernization, upgrading, and transformation. Look into the factors and mechanisms influencing human health and wellness and develop evidence-based solutions. And generate smart technology-based solutions for making urban operations and services more efficient, connected, and eco-friendly. We particularly value impactful collaborative activities in research and scholarship. PAIR researchers pursue research collaboration at different levels. In addition to interdisciplinary collaborations within and between research units, PAIR and its units establish partnerships with industries, governmental bodies, universities, and other external stakeholders. With internal and external collaborations, we have successfully translated PAIR-led innovations into commercializable solutions and practical applications, and established joint laboratories and research entities with external organizations, driving scientific breakthroughs, innovation, and technology development, and socioeconomic prosperity. PAIR's research excellence and research impact have been widely recognized at local, regional, and international levels. Our research outcomes have been published in leading journals, including Nature and Science. Innovations led by PAIR researchers have won prizes at various competitions and events, including the International Exhibition of Inventions Geneva. Many PAIR researchers have been named among the world's top 2% most cited scientists in their own areas of specialty. Individual researchers have been selected to the National Academies of Science or Engineering and as fellows of professional associations, and have been bestowed with local, national, and international awards and honors. Harnessing the strengths of PolyU's research and world-class scholars, PAIR will continue our unwavering efforts in research and scholarship, knowledge transfer, and collaboration to develop impactful solutions that benefit Hong Kong, the nation, and the world.
Good morning, Professor Wang, Professor Chen, colleagues, ladies and gentlemen. Welcome to this PAIR Distinguished Lecture Series. My name is Chen. I am the Director of the PolyU Academy for Interdisciplinary Research, or PAIR. It's my great pleasure to introduce our speaker today. Our speaker is Professor Stephen Zendi Chen from South China University of Technology, or CUT. Professor Chen is a world-renowned leader in polymer science and chemical engineering, currently serving as the Dean and Honorable Professor of the School of Emergent Soft Material at CUT. His expertise spans condensed matters in polymer, liquid crystal, surfactant, and hybrid materials. Through understanding molecular interaction and dynamics across multiple length, energy, and time scale, Professor Chen's work provides critical insight into molecular architectures that govern materials' microscope properties, enabling the development of the new electronic, optical, and function materials. A hallmark of Professor Chen's work is his pioneering research on giant molecular. He introduced an innovative approach known as the molecular Lego strategy, where nanoparticles serve as the building blocks that can self-assemble into complex macro molecular structure, including high-order superlattice. Remarkably, this self-assembly process is programmable, allowing precise control over molecular topology, composition, and molecular weight through molecular and mesoscale design. By reading just all his wonderful work, I find that I just have no idea what he's doing. It's so complex and deeper into the science. So I also read his abstract. I get a very little idea. But of course, his research has a lot of wonderful applications. And that make Professor Chen really becomes world leaders in this aspect. So Professor Chen has a very distinguished career. Before he joined the CUT, he spent over 3 decades at the University of Akron in the United States, where he served as the former dean of the College of Polymer Science and Polymer Engineering, and hold the titles of Frank C. Selvin Distinguished Research Professor and Trustee and Robert C. Musen Professor. So currently, at SCUT, he also leads the South China Advanced Institute for Soft Matter Science and Technology, which focuses on design, synthetics, and applications of high-performance soft matter. Professor Chen has received widespread international recognition for his scientific contributions. He is a fellow of many prestigious societies. There's a very long list I don't need to read, but I wanted to emphasize he's a member of the U.S. National Academy of Engineering. That's the highest honor one could get in this field. So without further ado, ladies and gentlemen, please join me welcoming Professor Chen.
Thank you very much, Professor Chen, for a very kind introduction. And it's my great honor and pleasure to be here. And this is the first time I visit your university, although I come to Hong Kong more than 100 times. Most of them went to the science and technology and go to other universities. And I'm so glad to see my old friends here. And Professor Wang, from broader perspective, you are my academic brothers. We all got our PhDs in RPI. So that's why the relationships here. Dongsheng and I have been good friends for many years, right? So luckily, he joined your guys in the last year. So that is a good move. I think it's a good move in this case. Now, today I'm going to talk about the superlattice engineering of the soft matter alloys in giant molecules. Look at the title, you will see a few words really never seen before, or very rare to hear this kind of thing. But after this lecture, I hope everybody understands and become expert, right? Today, I'm going to talk about first, and I would like to have an acknowledgement. In all my life, I have my former and current students and postdocs. How many? I have over 120 PhD degree students get a degree from me. I have over 100 postdocs and visiting professors and so forth and so on in last 30, 40 years. So without their intelligence and hard work, of course, I cannot say anything here. And also those pictures are the people collaborated with me for many, many years. And this is a long-term academic relationship. It's not crossover. I bump into somebody and then leave. No, they are for a very long time. You can see those are chemists, those are physicists, those are engineers, and all those people are simulations. They have many, many people. Somebody is older than me, somebody is younger than me, and I have a lot of people collaborate with this. Without their collaboration, certainly, your science journey is limited, all right? You have to have many, many people collaborate with you, then your science will go to broader and broader. The key issue is you have to get out from your comfortable area all the time if you want to do science. If you always stay in a comfortable area, you never achieve anything. So that is a key issue for me to say this. Now, where is our beginning? Everybody knows Freeman. These physicists also know him, right? In the last century, there are three greatest physicists around the world: Einstein, Chen Yang, and Freeman. All right? The Freeman, in about 60 years ago, he asked one very important question. He said, what would the properties of materials be if we could really arrange the atom the way we want them? This is a physicist. If you translate this language to chemists or material scientists, basically saying is I have lots of functional groups. I put those functional groups precisely on the scaffold. One-dimensional scaffold is a chain, two-dimensional scaffold is a sheet, three-dimensional scaffold is a subject. The question is, those summation of all those functional groups will become the macroscopic properties? The answer is no. Because you need to go through all the hierarchical structures. Those hierarchical structures transferring and amplifying those functional groups to become finally macroscopic properties. Right? I have former students working with me. They don't want to go to academics because you are working so hard. I cannot do it. So what they go to government agencies. For example, U.S. Patent Office, who is in charge of chemistry patent, was my student. All right? I asked him how many patents you will have, all right, basically for polymers. He said, well, polymers, 5 million, all the patents. All right? Then I will ask, all these 5 million patents are useful? No, it's not, absolutely not. 99% are not useful. Yes, look at the market. How many polymers are on the market? Less than 30. So the rest of them are all useless. Why? Because people imagine I get this functional group will get that property will not work. I file a patent, right? So that is the way which you will think about. So hierarchical structures in structure materials are very important. It's extremely important in this case. This figure I like a lot, but that is copied from a German website. The address is bottom there, right? You can see the horizontal axis is years, 1940 to 2040, that's 100 years as a one person's life. Nowadays, the life is longer, right? On the other hand, the vertical axis is from 1 angstrom to 100,000 nanometer. It's a 7 order of magnitude. For research, you either do bottom up, that's called the self-assembly, or top down, that's a lithographic method. That's either way you can do it, right? Doesn't matter you are engineers, you are physicists, you are biologists, you are chemists. You go to 2010 to 2030, all the attention goes to 1 to 100 nanometer scale. Why? Those I said, this is a structure in this length scale, basically determines the transferring and amplifying the functionality to macroscopic properties. So people's attention really on that size of the structures. It's not only atomic structure, it's not only molecular structure, it's even more, all right? People use supermolecular, all right? Those structures. Those supermolecular molecules will gather together to form a superlattice. That is the way which we will think about how we go from the atoms to materials. What do we do, right? Now, as you know, in the Science magazine, I call the Science is not journal, a magazine. Science magazine, they're forming 125 years. They proposed 125 questions in science. What is we really think about it? In fact, in the one of the questions say, how far can we push chemical self-assembly? That was one of the 125 questions, right? This question has been answered in biological system. Look at us, human beings, the highest self-assembly of the biology. Am I right? So in chemistry, people will always ask what I can do for chemistry to self-assemble to what I will achieve. Now I plot a figure like this. The horizontal axis is diversity. Okay, how wide it is, how different types. The vertical axis is a complexity, how complicated it is. Now look at the biological self-assembly and the chemical assembly. They are completely upside down difference. You see, for the biology, I starting from 20 amino acid. The self-assemble become alpha helix and beta sheets. Then go to the structure is a so-called primary, secondary, tertiary, and quaternary structure. Then they go further, go into very diversity, but also very complexity. Become, you can see butterflies, you can see all different things in a human being. They are all self-assembled, the result of self-assembly. Look at the chemistry. As I said, you have over 5 million patterns. You have so many monomers. At least you have 2-3 million type of monomers appears. Such a complex startup. Then you have self-assembled for such as diblocking polymers. You have lamellars, you have cylinders, you have double gyroids, you have a BCC structure of spheres. Then you go further. That diversity becomes quite wide, but the complexity goes down. All right? So this is completely upside down system with biological self-assembly. Now, what the important key is, look at the cross point of these two chains. The cross point of two chains is self-assemble, is 1 nanometer to 100 nanometer. If you, from chemical side, you go downwards, go to that point, you go upwards, then that is our goal we have to achieve. Right? That is the most important message I'm convey this one. What's the reason for that? The reason is very simple. For human evolution, you can see any complexity will gives you the new functions. Right? That's a human being. It's like this. But for polymers, for our chemistry, very different and complicated molecular design goes to similar situation, similar functions. So the situation is natural evolution, a complexity equal to emerging different functions. You have more complication, you get a more functionalized system. For us, polymer chemistry design is complexity is not equal to functional difference. So what we have to do, we have to really challenge of the precision polymers or chemistry, how to based on precision design to fulfill targeted functions, to find those new functions. And nowadays in material science, there's a one word that is magic called metamaterials. What's the definition of metamaterials? Chinese called 超材料. Why it is so? Well, that defined is in nature, we cannot find the properties of those materials we call the metamaterials, all right? For three-dimensional photonic crystals for them, all right? One-dimensional photonic crystals, butterflies, you can see different color changes, right? But three-dimensional photonic crystals in nature, you don't see it. If you can produce the three-dimensional photonics, you will see actually so-called metamaterials. All right, negative birefringence, negative refractive index materials, that's another metamaterials, and so forth and so on. You have many issues on this. These functions, how do we catch it? This is a very important issue for material scientists and for those who really very good for chemistry. Now, what I'm approaching here is about 670 people, right? Everybody has its own way to make self-assembly, all right? But what my self-assembly methods? Well, I'm old enough to have grandkids. So the gift I give them, every time they say, Grandpa, do you have a gift? Well, okay, I have Legos, right? The Legos quiet them down to making all those structures and the different subjects, then I can relax a little bit, all right? So this one. So we call the molecular Lego approach. That's what I approach is. Each Lego parts, I can design the molecules to forming these particular parts. Then I'm making the interactions between those parts making them to forming a structures which I like. All right. So this is basically both chemistry and the physics concept. Then you also need the engineering to this. All right. So the key issue to chemistry, wow, precision, precise chemistry. If here anybody who does polymers, I am sorry to tell you, the polymer way to polymerize materials are all not working here. The reason is because the precision I need is not only chemical structure, but also composition, then sequence, then topology, and then size. All right? So I always telling people when I in India to give a lecture, I always say, I have a basket. There's all snake in there. They are same identical type of snake. For polymer people, is you randomly pull two snakes out. They are same type, but the size is different. That's called polydispersity. All right? But the polydispersity in my side is not allowed. You cannot. So polydispersity equal to 1. There's no size difference. All right? So for biological people, in our human body, condensation polymerization always happens in our body. But in polymer people do condensation polymerization. The theoretical equilibrium condensation gives you the polydispersity equal to 2. But in our body, all polydispersity equal to 1. Nothing changed. Every molecular weight is identical. So this, I listed so many chemical reactions. I don't want to go details. Otherwise, this slide I will stick on for 2-3 hours. You can see the key issue I want is organic chemical reactions. So clinical chemistry or other efficient transformation is key for me to generate the precision polymers, the precision molecules or precision giant molecules. On the other hand, in physics side, I needed to build up interactions. Interaction, many supermolecular people, like your advisor, Takuzo Aida, or Bert Meyer, those people, they will think about is also non-covalent bonding, all right? Yeah, yes, but you will think those bonding are physical bonds. Physical bonds, bonding energy is much weaker than chemical bonds, am I right? So what are you going to do? If you have those weak physical bonds, you stick them together, will not be so strong. You will think, oh, that mechanical property is horrible, all right? But you have to think what I do. Yes, hydrogen bonding. Bonding energy is 30, 45, 50 kilojoule per mole. Compared with carbon-carbon single bond is 145 kilojoule per mole, all right? So it's way, but it's no comparison. However, in one point, I put 10 hydrogen bonding on that. 30 times 10, 300 kilojoule per mole. So it becomes strong bonding, right? So you can do this by design to making those case works in this case. So that is superlattice engineering to generate the hierarchical structure, which I want to do. Now, this is the giant molecules we call the topological hybrids. Those are the people who in the last 10 years who involved with me to develop this technology, right? And this side from top down, the first one is in Peking University, the chemical college now is a vice dean. And then the second one is Coca-Cola Material Research Laboratory Director. And Yu Wenli is, Dongsen is your friend, right? And he is now in Sichuan University. And Xue Huidong is in South China University, a professor. Kan Yue is in South China University. Mingjun is also, Ziwei is also, Zhang Wei is in University of Pittsburgh as a professor. So you can see all these people are starting involving developing. But why people say, why I view these guys as so important? Because listen, I got my bachelor degree in mathematics, in pure mathematics, okay? I got my master's degree in chemical engineering. I got PhD in chemistry and material science. You can see what I spent 15 years, start from a mathematician to finally become a material scientist, right? But this way, it's a very hard way to do it. But during this way, I need a lot of people to help. Those people are all from Peking University, South China, East China Science and Technology, all those good universities. But those people helping me tremendously to build up an organic research group in my groups. That is a very important issue because I want to design the molecule first. First of all, you have to build up, right? That's the chemistry. Then you have to do physics in our side, all right? So, sorry, I haven't. But what is giant molecules? Giant molecule has a couple of different things. For example, the first one is shape amplifiers. When you listen to amplifiers, you will think hydrophilic versus hydrophobic, different. But here in not, I say shape amplifiers. For example, I have a sphere connected with a rod. This molecule put together, what happens? Sphere goes with sphere, rod goes with rod. All right? This is called like principle. Okay, translated into Chinese, it's much more beautiful. 物以类聚，人以群分. Translated into English, likes like. There's no feeling about it, right? So also you can have a giant polyhedron. The simplest is tetrahedron. The tetrahedron has 4 corners, all right, 4 tops, right? These 4 corners, you put 4 different molecules on there. You can see hydrophobic, different hydrophilic, but more importantly, at the 4 corners, you have 4 different molecules in there. Your polyhedron becomes chiral tetrahedrons. All right? The chiral one and the non-chiral one has a very different properties, at least optically. All right? Then you also have a giant surfactants and the lipids, like here. You have one head nanoparticles with tail polymers. You have one head multiple tail. You have one tail multiple heads. Head could be hydrophilic, tail has to be hydrophobic, or tail has to be fluorophobic, and the head will be hydrophilic, and so forth and so on. You can play a lot of games on there. Okay? By this one, you're making them assemble. What happens? Right? This is a way which we design the molecules. We're making them assembly. We will see what happens. Here is a basic knowledge. I'm telling you what it is. If somebody not in material science, you may not know this. As you know, metal alloys are very popular in industries. All right? The metal alloys started in 1901. Start to develop thousands of different metal alloys which found their properties are better than metal itself. So metal alloy is very useful, all right? Among these metal alloys, they have one group of the metal alloy called Frank, here, Casper metal alloys. Frank is Sir Charles Frank, Bristol University in England. Casper is GE research, Central Research. It's very close to our RPI place, right? 17 miles away from us, Schenectady, right? They both studied alloys. Metal alloy they found. When metal alloy structures, first they form a tetrahedron. They form a tetrahedron, then they pack into structures. This we call the Frank-Casper phase. Frank said, okay, in one falling atom, that's a yellow one, outside, I have closer neighborhoods with 12 coordination numbers. That's called the Frank polyhedron or Frank lattice. Then Casper said, no, it's not only 12. I can have 14, 15, 16 neighbors in there. That's called the Casper lattice. You're making Frank lattice and the Casper lattice put together. You're forming Frank-Casper metal alloys. When I got my PhD degree, I think Professor Wang at the time was in elementary school. And then you will see, actually see C15, A15, C15, sigma phase, Z phase, those are all the Frank-Casper phase. During my time, those NSF, National Science Foundation, supports tremendously money pouring into the Frank-Casper lattice. Why? Because the A15 structure is superconductivity. The superconductivity is A15 phase. So lots of people focusing on this one. So when I was taking class X-ray diffractions in material science and engineering department, The teacher stand here was talking in whole semester. Each class, he talks one structure. So whole 32 structures talk 32 different things. That's it. All right, because his research is focusing on the Frank-Kasper phase in this case. All right, but you see, Russian has a very good mathematics people. Mathematicians, what they plot, they found out, they say, okay, look, I put the horizontal axis, the average coordination number. Smallest coordination number is 12, all right? Largest coordination number is 16. So all the things are in between. So the average number in between. The horizontal axis is when coordination equal to 15, how high percentage it is. Then they plot, suddenly they found that's a triangle. The experimentally observed 28, the Frank-Kasper phase are all fall into these triangles. And the three corners, okay? The corner, one is the A15 phase, one is Z phase, one is C15 phase. These are three basic structures. Rest of them are all these three types of structure combined together. So Z A15, this line, I call the plateau line. And the C15 line, I call the non-plateau line. Later, I will tell you why there is case, all right? Those structure for this one is called Frank-Kasper phase. That's found very early ago, 1974, by Russian people, all right? Then we will see why, first of all, I will ask in 2 dimensions, the tiling. For plateau tiling, you can see triangle, square, hexagon, they can put 2 dimensions are beautifully covered. Am I right? No any defects. But if regular pentagon, what happens? You really have problems, right? You either have empty space or you have overlapped space. So in classical crystallographics, 5-fold symmetry were not allowed. Well, get out, all right? If you are a good student, listen, if professor were telling you regular pentagon doesn't work because it cannot cover 2 dimensions, all right? If you are a good student, you will say, okay, but how my surface look like these 5 regular pentagon can be covered the surface? You need the curvature of 72 degrees. Then all this pentagon can be covered on the surface. That is basic quasi-crystal principle. That's the year 2009, which got the Nobel Prize. All right, so that is the case. So at this moment, the classical crystallographics say no pentagons, but currently the modern crystallographics, no, that is also included in our crystallographics. In this case. However, I'm asking is why metal alloys is better than metals? This is a question, answer very clearly. I have 4 equal size of the spheres on there. That's a metal crystal, right? This tetrahedron is a regular tetrahedron. Then you put them together, you will see they never get out of the 3-dimensional structures. They have so many defects. In order to overcome those defects, they have to pull away, making this regular become non-regular, right? If I have a structure like here, you have 1 bigger one and 3 smaller one put together. Well, they're forming beautifully the 3-dimensional structure. So thermodynamically, metal alloys is more stable than metals. So property-wise, also you have more defects, I have less defects in this case, all right? So why metal alloy exists is because thermodynamically they are more stable in this case. By saying this, then let's go further. Our soft metals. Soft metals, this is 4 groups. Besides us, the 3 groups are all our friends. Now, in this area, we are not a very big area because this is a very difficult area to do. You have to synthesize, you have to chemistry, you have to physics. But these groups are people, we are like each other, so we're supporting each other. The first one is Virgil Perchik. Virgil Perchik, everybody knows he is a tough professor, right? Treating students like a slave. It's a really bad situation. But actually, this is very pure scientist, right? He's seeking for the highest, the precise structures. He did using genome. So he found A15 in the sigma phase. Frank Bates, my good friend at Minnesota, he using diblock copolymer. He also found A15 sigma C14 C15 phase. My Indian friend using small molecule surfactants also find those structures. In our group, also we found those structures. People will ask, why this one? Because people found immediately those structures equivalent to Frank-Casper lattice. The two molecules, two atoms, size is different. So they form alloys, right? Size they are different. But why they always find this one? People found out that these structures, the size differences are very small. The volume ratio between two sides is about 1.01, 1.02, 1.1 up to, at most, all right? So look, I said a few things here. In metal alloys, you need two or more type of atoms put with different size and electron orbitals to put together, right? But in soft metal, we only using one component to become forming this structure. How can? All right, this issue is very much bothers people during year 2000 or 2010 in this case, all right? So why it is so? Actually is when you're forming a sphere structures, you don't only has a one molecules. You have a many molecules in there to forming a one building block as a sphere. Then using this sphere, then constructed to the structure Frank-Casper phase. That's why the superlattice is. Why superlattice is so important? Remember, if you look at the atoms, what size they have? Less than 1 angstrom. Look at me. How big the size is? Nanometer. Okay, at least 5, 6, 7, 8, 10 nanometers. So therefore, the size differences compared with the volume is 1,000 to 5,000 times bigger than the normal crystal structures. Is that useful? Of course. Because atoms size, you reflect X-rays. My size, bigger one, reflects visible lights. So you can really affect lights. You really affect lights, then affect the sounds, affect then reflections, affects with electrics, magnetics, and the light. Everything reflects. So you are going to the words is going to the metamaterial size in this case, right? So what we do is we actually forming these bigger particles. I need many molecules. Now, statistically, you have a one molecule more, one molecule less. Your volume changes, am I right? And also, because you are in soft metal, those spheres are soft. You can be squeezed. You can be deformed. They will deforming different type of polyhedrons, right? In this case, you will always find A15, sigma, and C15 phase in this case, all right? Now, we did it this way. You can see I designed all different molecules. You can see all kinds of molecules synthesized. Each sphere, how many molecules are containing? The smallest 18 molecules together. The highest is 31, 38 molecules. See, you take one out, put one in, the volume changes very little, all right? Then they only form A15 sigma phase, nothing else. The next step is, how do I go to making the volume ratio become bigger? That is this guy, Professor Su, sits there. That's his PhD thesis. He came to me and said, Dr. Chen, the first approach is making all the spheres only 4 or 5 molecules. You take one out, put one in, you have a 10, 20% volume difference, all right? That's a good idea. So he succeeds. Published in Nature Materials, Chemistry in his paper, right? So in this case, so what do? I give you one example, more recent example, after his graduation, right? This is another one. I pick up this material, making everybody nervous. because it's 5 folds. 5 folds, nobody wants to touch it. It's like a ghost in crystallographics, all right? But I purposely pick up 5 folds of materials. It also core is those funneling groups and those this one. So you will say, oh, how do we do? You're assuming that we're stacking a column, all right? Because pi-pi interaction. Yet I have out corners, those nanoparticles, size is 1 nanometer in size. Pi-pi interaction in how big a distance is? 0.4 nanometers. So what happens? You try to stack up in the columns, but it's go 3-4 molecules stack, broken. 3-4 molecules broken because outside too big, all right? So outside will fall up and fall down, become sphere. Every 3-4 molecules will do this, all right? So that becomes a column, but it becomes fragment of the columns, right? You do this way. If you do this way, now we can see the synthesis, NMRs, GPCs, multispectroscopies, everything prove I only have 1 molecules with this molecular weight is over 10,000, all right, in this case. Now we do this. When we do this at high temperature, these 2 gentlemen, both are PhD now, and the top one is American to be a postdoc, and the bottoms is MIT postdoc now, just come back to our university as a professor. And you can see we get the structure, X-rays and electron microscopes. That is mu phase, is a trigonal phase, all right? Why I make it determine so quickly? Because I have X-rays. Then I pull out all the libraries of the Frank Casper phase in metals. Compare. This is exactly fit, all right? So I know this is a mu phase. But in order to prove that it is truly the mu phase, I also will do is, wait a minute. That we also do look at the transmission electron microscopes. They also give you the real space to see that is a space which we observed as a lattice. So this is done. When they come to me, say, Dr. Cheng, we find a mu phase, metal alloy has it, and the soft metal never seen before. I say, that's good, but not great. You have to find something metal alloy never see it. That is most important, am I right? So do this one. I say, why don't you cool down the temperature, see what happens? That's this. Then Chinese students, if you have any Chinese students, you have to really take out these bad habits. All the Chinese students get the results they don't know. They put the drawers, don't tell you, okay? Until all the graduation, got PhD. By the way, Professor Chen, we have some results which we don't know what happens. See, because they are afraid of solving it before you graduate. Oh, all right. So that's a problem for Chinese students has habit. American students, they have something, we're jumping to our desk, something new. Okay, so this is a habit I don't like to have. This is the same thing, he got it. Take all the libraries, come up, nothing fit. All right, this is what happens. So we said, first of all, you have to prove it's metastable or it's stable. How do you prove it? Go to synchrotron. If you're heating up, you have a 5-phase, go to mu phase, but it does not say 5-phase is a thermodynamically stable. Why? You have to cool down from mu phase, go back low temperature, they will transfer to 5-phase. That indicates your 5-phase at the low temperature is thermodynamically most stable, and the mu phase at high temperature is most dynamically stable. Okay? If you do this one, we find out, okay, that is 29th experimentally observed Frank Casper phase, we call the 5-phase. All right? Of course, everybody is happy with this. They hope that they can publish a good paper. But you see, look, university generates students. University do not really think about the scientific research or publishing papers. They are secondary. The key issue is students you have to generate, all right? So you do this, we do the X-rays, do electron microscopes to prove all what we do is right. And also in triangle, you can see the mu phase is on ZC15 line. I call the norm platonic line. And the 5-phase is in the middle. Why? The 5-phase has all 3-phase structure combined together. Okay? So in this case, when I got this one, write a paper, then the review comments come back. Say, Stephen, this is wonderful. All right? Metal alloy, never see it. You found it. But what's the importance? People ask me, what's the importance? Then I say, okay, let's study what's the importance. Look, A15Z phase, I say on that line, I say is a Plato line, right? What the Plato line mean? Means it's a square and it's a rectangular, it's a regular rectangular. You put these two structures together, you get the H phase is 3 power of 3, 4 power 2. What does that mean? Each lattice point, you have 3 triangles and 2 squares. You look at it, try a few minutes. Every point has this structure, right? But they have another arrangement. It's down there, it's sigma phase. You can see 3 power of 2, 4, 3, 4. Each lattice point, you have 2 triangle, 1 square, 1 triangle, 1 square. Look at it. All right? This is Plato line, no problem, because it's only square and a regular triangle. All right? Then you can see the Z phase and the C15 phase. What happens? Z phase and the 15 phase, you can see no longer square but rectangular. And the C15, the triangle, is abnormal triangle. It's not the equal lengths and angles. Right? When they're put together, you have a mu phase. We just found out, all right? That mu phase is also 3 power of 3, 4 power of 2. So you can see each lattice point, you have a 2 rectangular, 3 triangles. Am I right? But when they become downwards for 3 power of 2, 4, 3, 4, you have 2 cases. One is rectangular with normal triangle. Another is non-rectangular, is square with triangles, so normal triangles, right? So that is the case. You can see for that case, P sigma is there. But for another case, in metal alloys, it's missing. We have in there, it's 5-phase. We fill in the space which was missing before. All said this one, I submit again. There's Stephen, beautiful. But why you don't see the metal alloys? What we see your soft metals? Well, revision again. Now we have to do things, what do we do? We say, okay, we try to this one. We're using the Wegener sensor theory to approach to make every sphere now become polyhedron and look at their volumes and look at their shapes. BCC structure is only one volume. All right, that's no problem. Mu phase, the distribution is more broad. For 5-phase, it's very broad. All right, the shape and volume ratio is very big. You see, the smallest ratio is 1, the largest ratio is 1.44. So that means the size is very different. All right, that's just one. But the more important from shape, for BCC is only one shape. Means the long axis and the short axis are identical, equal to 1, right? But for mu phase, oh, they are slightly different. But look at the 5-phase, is 1.22. So that's very clear. Now in 5-phase, the structure can be squeezed, deformed, become ellipsoid. It's no longer sphere. In metal alloys, outside the electron orbital, you want to deform it, how much energy you need? Huge. But here, we are soft metal. You don't worry about it. They can be squeezed, can be deformed. So we found that, and in metal alloys, cannot be found. And one review comment even more. Say, Stephen, think how many Frank Casper phase theoretically exist? I said, well, let's calculate. Over 90. Okay, structure. Then how many experimentally observed? 28. Now plus 1, 29. Why rest of them cannot be found? Is because in computers, they don't worry about shapes. elongated, ellipsoid, even like a tube, no problem. But in reality, you cannot be this way, right? That is the case. Now, of course, I am telling you now, volume ratio around 1, volume ratio around 1.1 to 1.4. How about the larger than 1.4? This way we're not working, okay? Making decreasing number of the molecules in each building block networking. How do you do? Polymer people are very smart. Say, okay, let's blend A plus B, all right? But this A plus B is not the equal common blending system because first of all, they have to form sphere. So A has to go with A, B has to go with B, become two different type of shapes of the spheres, then they co-crystallize together, all right? So what do we need? The core of A and B have to be very different chemistry. They have to be identical. Yet the periphery has to be identical. So you're forming a sphere outside the chemistry are identical, they still can be co-crystallized. All right? Using this design, let's do it this way. Okay? So we have three choices. We have a polymer, we have a dungeon, we have a crown and a disc-like. We're using second and third one because polymer is too soft in this case. All right? In this case, you can see the fragment design is this one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4 are core. 5, 6 are shear outside the periphery. All right. All this you can see the T shape. The T is click chemistry. That means I guarantee the efficiency of 100%. Every molecule synthesized identical in this case. All right. If 1 act with 5 becomes blue ball, which is bigger. 2 react with 5 become green ball with the middle size. And 3 plus 6 react with the yellow ball with smallest. And also 4 react with 5 become dungeon, become the largest is sphere in this case. Okay, then let's see. If individually they are all BCC or F15 structure, no problem. But you mix them, look at. Volume ratio is 6:1. What happens? This is phase diagram. You see the yellow area is aluminum boron. You see the red area is sodium zinc 13, all right? And you decreasing 4.321, then you get actually the same thing, but the compositions are very different, right? I can prove this one using X-rays, using transmission electron microscopes. Now, I further decrease to 2.621. I got the C14, C15 going back to the Frank Casper phase. Okay? Then people say, oh, how far you can go? This is another my friend, Bert Meyer, Eindhoven from. He said, Stephen, tell me how far you can push to this design. I say, I can push to 10:1. All right? How do you do it? This is the structural report. 9:1. Sodium chloride. Salt. All right? The sodium chloride we can do. Now, this is in the beginning, we come to 24. So actually, nowadays, we can get all of them. You can see from 1 to 10, all different structures we will see. See, below 3 are Frank Casper phase. Above 3, physicists called is quasi-Frank Casper phase. They are no longer no longer as a tetrahedron as a units, but they could be octahedron and all sorts of as a units to do this. You can see this one, all right? So all these type of things, I say, if non-self-sorting, A and plus B, they mix together already. I can also do, look, this is 10-fold symmetry, decagonal quasi-crystal, never been found in soft metals. We first found out. This is a non-self-sorting process to receive this one. All right? Now, this is metal alloy tables, AMBN alloy. All these structure I can give to you. If you want that structure, tell me, I design molecule, give to you this type of structures, all right? By saying this one, you say, Dr. Chen, next research topic, high entropy crystals. I have 2, now I have 3, I have 4, I have 5, okay? high entropy glass, high entropy ceramics are very popular, but then nobody say high entropy crystals. This is a high entropy crystal, next step to go, right? But before that, I have two red arrows. These are two very specific metal alloys, which are very difficult to find. The one is, you can see, the A6B23. A6B24 is AB4. It's a very simple structure, right? But the A6B23 have one molecule missing, one atom missing, right? In this case, how do we do? The second is gamma brass. Everybody knows the gamma brass. Gamma brass was found in 1926. You can see gamma brass is 5 copper atoms with 8 zinc atoms together. It's so useful, all right? 黄铜相在中国，对不对？ That's a very useful industry, right? Then, after years, people found suddenly the gamma brass crystals within the nuclear cell is solid solution. What happened? You can see 3 iron atom, 10 zinc atom also give you gamma brass. Then you will see 9 copper atom, 4 aluminum atom also forming gamma brass. Then people found gold, silver, titanium, every elements were forming gamma brass. That indicates in gamma brass, the lattice point is the same. But what molecule, what atom occupies this lattice are random. That's called solid solution, right? Then in our case, how do we do in soft metal, right? Then you will see, this is A26B6 or A6B26. You can see for this particular design, for 2 mixing. But specifically, this is interesting, it only takes place in composition of 20.6%. In metal alloys, this is called a line compound. In phase diagram, everything have a certain phase diagram areas. I have this phase formation, right? So-called a line compound is on the line, a single line. Only at this compound, you're forming this structure. You deviate from both sides, will not see it. This is the line compound. Only 20.6% of a B component, it's forming the A23B6 structure. All the structure characterization are in there. If you look at the gamma brass, I use the tetrahedron with a disk mixed together in 77%, I see the gamma brass. All right, the gamma brass, you see, in soft metal gamma brass found is 100 years after the gamma brass observed in 1926 in this case, all right? So this is a phase diagram from soft metal compared with the metal alloys. Very similar, all right? In the beginning, BCC structure is a beta brass in structure in this case, all right? So people will ask, what's useful? How, you said so many things. Is that useful? Yes. Yeah. Today, the same time, and 发改委, I don't know how English say, is in our university, examining what we do in this project, because they gave about over $100 million yuans to support this project. You can see what we do. This is, I collaborated with Taiwan, did this one in the beginning, starting year in 2013. That's called the directional self-assembly. Actually, it's a non-lithographic method. We do this one, okay? Then we're using design of the giant surfactants with top is inorganic, is porous, and tail is organic like a polystyrene. Then we do design for this one. We did is the size now is about 6 nanometer. And the smallest one is 4 nanometer in this case. Okay? Now, if let them stand up, becomes a lattice. The lattice distance could be 8 nanometers. This is very important in storage chips, all right? And this is very important in the normal chips in this case, all right? Intel has announced using this method combined with the lithographic method to build up their new generation of the new chips. The new chips now is just announced. Their stock market jumping to about the 8 to 10% times, right? Remember, Intel 9 months ago was announced by Wall Street, say this industry is dead. That company is dead, but they recovered. By Cheng Liu, right? Malaysian citizen, right? For chips making, very beautiful in this case. So that is good as even better than normally now we're using the so-called lithographic methods in this case. The reason is because inorganic, organic, when you etch it, inorganic will not do anything, but the organic one will be disappears. So it's a very easy to do this one, all right? So this one is very, very, very nice technology. And International Chips Association has announced this method is the next generation of the chips making. Of course, Ashmere doesn't like. I went to Dutch many times. Ashmere hear this one, say, Stephen, you are beating our business. Because they invest so much money for Ashmere to making the lithographic machine, right? Now you are something is not using them. So that is the situation we are doing. This is one of the applications you will see. Now, in summary, what I do is I give you the molecular Lego approach in this case. I can build up all the things, right? I haven't said too much about the three-dimensional photonics and all those issues we have developed in many cases in this case. But basically what I'm going to do, I'm going to establish two files, two libraries. One called the structural sensome, one called the functional sensome. Functional sensome means if you want that property, you need this functional group. Structural sensome means you use my structure. Your functional sensome can be amplified, transferred to become macroscopic properties. If these two files are working, that's actually AI approach. Therefore, you can see the future, I don't need the chemistry. Everybody coming to pick two, put together, that's advanced materials. All right? So that requires precision chemistry, precision physics, and precision engineering, which requires physicists, chemists, biological scientists, and engineers really working together. Thank you very much.
Oh, Professor, we still have Q&A section.
Oh.
Okay. Yeah, dear colleagues, students, it's my great pleasure to moderate the Q&A section. At the beginning, I think I would like to thank the Professor Cheng for his wonderful, insightful talk, which combine the beauty in mathematics, the diversity in chemistry, and also broadness in application. I think his talk and his work really open a new area, for future development. So now, let's first welcome any question from audience, and then we also have some question online. Okay, any question from the audience? Okay. Okay, Professor Liu.
Stephen, every time I got a lot of new ideas about your talk. So when we talk about this crystal structures, and have you thinking about use the protein structures, and so we can just make any kind of morphology and also the different molecular contribution at different part.
Your question is actually, many people ask me this way, all right? And in fact, the protein structure we tried also. So first of all, protein structure prefer in the water. So you need a solvent. I here has no solvent. Everything is in solid states, okay? The second, protein are not really sustained in the high temperature. Here, those structures, I need some high temperature to do it, right? But I tell you another application which I am doing. Remember, I said core and share, all right? In the core, if I build up an organic basket, then I put the quantum dots inside. The same thing as outside, I can build up structures. Then you shine the laser. What happens? All the quantum dots reacts in an ordered, three-dimensional ordered fashion. It's never been happened before. Okay? Then you will see how that will work. And also, if in a basket, I put 苯中糖是 those molecules in there, I can control the number of molecules inside. Right? Then I can answer the questions they never answered. How many molecules put together you have AIE come up? Right?
Yes.
So they have many, many issues to do this, right?
Okay, thank you. Very interesting. Maybe we can try that.
Try it. Yeah, you can try. If we can collaborate, do this way. It's very easy, right?
Okay, thank you.
Thank you very much. Any more questions? Okay, there's one question. Oh,
Yeah.
okay.
Yeah, thanks, the wonderful talk for you, Professor Cheng. And
By the way, probably mention your name and
Oh.
department. I know you, but I think it's better to.
yeah, I
Yeah,
just
yeah, okay.
introduced myself
Yeah,
to
yeah.
Professor Cheng. I'm the new assistant professor from the ABCT, the Department of Chemistry.
He
Yeah.
was Zhao Dahui's student.
Oh.
Yeah.
Zhao Dahui is the person I introduced him to back to Peking University.
Okay.
I'm the scientific grandson level for Professor Cheng. Yeah, and I'm now processing the conjugated polymers application in photovoltaic devices area. Yeah, so well, we are just focusing on some surfactant layers. Yeah, for the devices application. So I have some questions about this kind of supramolecular assemblies, whether this special phase has some specific or specialized application area. For example, due to some special packing mold or some special assembly structures.
They have many, many different applications. I give you one application, which I do for American soldiers. For giant surfactants, right? The head are using the POS, SiO 1.5, right? At the 7 corners, I put on the zooionic molecules. So then the tail, I put the biodegradable molecules with 抗生素在后面. So in the war, 95% of soldiers died by blood lost. So blood lost, how they can treat it is they're using the type of the silicon SiOX, those particles, put onto the wound. If you build up the network, you survive. If you don't, you're dead. All right? Also, if you survived, then 65% will be still dead. It's because of infection. If you're using our silicon SiO 1.5, the surface area is 1,000, is a 10 to the power of 7 larger than those normal silicon particles. So they can easily to distribute on the surface. And then they're forming the network. Then the zooionic materials will forming the negative charge. So the bacteria were afraid to put onto the surface to make infection less. Then you gradually degrade the polymer, release the drug to further prevent infections. All right? 这是美国陆军的 topic. All right? Don't write anything, but I'm telling you what the application is. That's one of the applications. Okay? You have many different applications in this area, right? As you know, nowadays, you are really doing computer. The computer is electronic computer. The electronic computer basically are two basic, very important parts. One is the 二极管 dial. Another is amplifier, 三极管. In next generation of the optical computing, how do you do the optical dial and optical magnifications? How many people think of this way? Almost nobody. Okay, I'm thinking deeply around this using my way because I'm using silicon. Silicon oxide, you shining UV and ozone become silicate. What's this? This is ceramics, poly, glass. Am I right? So there are many issues which we are thinking about, right? Many people say, Stephen, you are so old. All my friends in America, everybody see me like an enemy. They say, Stephen, we hate you. Why? We are lying on the sandal and relax and do nothing. You are still working. You are pushing us like hell, right?
That's right.
Well, that's the situation. I told them, you guys can work. If you want, I give you a job, all right? Oh, no, we are relaxing, all right? So this way. But the situation is you have to always thinking and out of your comfortable line. Okay, you push yourself to continue to learn new things. Then you will be always good for that. Okay?
Any more question?
Yeah.
Oh,
Okay, Stephen. So thank you for your.
by the way,
Yeah,
introduce
nice
yourself.
briefing. This is BG. I'm from the EBCD. I'm the chair professor in chemical biology. Also doing some the imaging study. It's good you mentioned Benjong. He's super nice the EIE the structures. That is all these questions we chatted before. How many aggregate molecule can produce some certain amount of the fluorescence? So far, it's very hard to answer. So yeah, by using your system, maybe can make it. So which is good. I will discuss with the Benjong end of this month. I have an imaging conference, by the way, end of this month.
You know Ben?
Who?
You know Ben Zhong?
Yeah, very well. Yeah.
He got into the Hong Kong University of Science and Technology, the reference I wrote.
Oh my goodness.
Until he becomes a full professor, every stage I wrote his recommendation.
That was the 1990s, right?
Yeah. Okay. I know him very well, right? So I haven't talked to him this idea yet because I'm afraid he's yelling to me. Invaded his area. So I'm not doing too much on this case, but it can be done. Look, organic, those like a the Benjong data, right? The light is relatively weak.
Yeah.
So in BIOS, it's useful. But in optical communication, it's too weak. So I am focusing on optical communications. But also, I like to see Ben's work to be further developed. That would be great. I can tell you the limit of those AIE. You need how many molecules? 2 or 3 molecules you need.
A lot of
emit lights.
limits inside, I think, are hard to solve by right.
Yeah, that's it. So I have a way to do it. So it's very easy. Okay. So the BIOS, although my wife is a biologist, but I hate to talk to her about this issue. Yeah. My youngest brother is a very well-known medical doctor in the United States.
Okay.
His wife is an NIH program director. So he always telling me all those, your area, the system, what happens, right? So your area is very important because medical insurance and biological studies during last 50 years have developed so fast, right? So people now, America just announced that cancer becomes 慢性疾病. is no longer emergency stuff, right? That indicates that the developing is very quick. I think it's your guys' research is really meaningful.
Yeah, thank you. So actually, I'm thinking, because your system superlattice, you need to have a precise design, right? I think with very deep the knowledge. But we thank you so much. So at the beginning, you mentioned after your talk, people will understand your presentations. One of the witness, I understand your topic. So, for example, now in the cell biology study, so previously people know the protein, people know the organelle, suborganelle, this and that, and so on and so forth. But in recent years, people more care about the physical chemistry change inside of the cell structure, for example, liquid-liquid phase separation.
Liquid phase
All
separation.
right. So I'm thinking for
your guys are using liquid phase separation is not scientifically sound because you are not under thermodynamic equilibrium.
Hey, I want to hear more details. Can you
Be careful.
give more
This
briefing?
I warn everybody. I have a young professors in my group is doing this. In my research, our college is doing this one. I tell him using this word has to be very careful because physical chemists were jumping on your table. Human body is never in the thermodynamic equilibrium. All right. So you are in non-thermodynamic equilibrium using thermodynamic equilibrium principle to have describe liquid phase separation may have a problems. So you have to be very careful.
The superlattice, the system.
We are in thermodynamic equilibrium because I don't have a solvent.
Together.
I have no solvents, right? Everything's chemistry, peripheral chemistry is identical, so it's no problem. Okay, so that is the issue.
Yeah,
Okay.
thank you. Well,
Yeah. If you want to know another applications, I'm using the quantum dots in there to control the quantum dots and the quantum dots distance, 量子场景. I can do all other things.
thank you.
Okay, there's one question from online.
Okay.
It's written in Chinese. I'm not sure I can capture the meaning. I read it in Chinese first. 介原子体积不对称性是如何影响巨型分子软合金超晶格相态演化?
This guy really knows what I'm going to talk about.
Basically, the volume non-symmetry of matter, methyl atom, and how this affect the.
Here, basically, I saying those all what the particle I described is sphere, right?
Yeah.
Sphere squeezed by neighbors become polyhedral, right? But also you have volume asymmetry. The volume asymmetry for this particular case, you have from perfect one or identical volume size, you get a BCC structure, right? Or you get the FCC or HCP structure anyway, right? But then if you can volume asymmetry goes to the sodium chloride, that's 10 to 1, all right? Sodium chloride is sodium atoms and the chloride atoms volume 10 to 1. You will see the structure difference. Then I ask myself, how far I can approach to the way large sphere and small sphere will be separated. They don't like each other. Finally, separate each other. I don't know yet, but I'm working on for this particular case. All right.
Okay, Professor Cheng, you mentioned the DSA application. DSA. In addition to that, which kind of promising application you envision, for the new material you discovered?
Because in this case, you don't need Guanke right? You don't need a lot of other things to do this. And you don't need the lithographics in this case. You can do all the structures, right? The way which they do is, first of all, they have a couple of a model piece. They design the structures by microstructure level, because you can do this by amplified and do this, all right? Then they go through not magnify, but the shrinking type of like a opposite of the electron microscope. So you have a big ones, you go down to the nanometer, then you put on the chips. That is basically the principle of the lithographics, right? But you shrink it, it's not easy. Okay, you need 31 reflections by test. Only test not do it. Nobody else can do it for this particular case. Then they go to the nanometer, they have distortions. Then distortion, you cannot repair it because it's a nanometer. You cannot see it, right? So the distortion has to be very, very limited. So you go to smaller size is not only the light beam goes to the shorter wavelengths, right? The more important is you have to make this distortion become smaller. So you have a two line, you're going down, become two line crossover, you're dead, right? So that is a very important, but in our case, you don't need it, right? So actually, no, I didn't bring my computer. I have a whole set of the PPT talk about these issues. I can show you what we did and what using lithography did, right? It's very clear, right?
By the way, I think many faculty position in Professor Cheng's institute, right?
Yeah, I want your student.
Yeah. Okay, good. I think the salary is comparable to PolyU EP position, I think.
If you really want to know my position here, now this is a person just come from Professor Aida's group.
Oh.
He was my
From Japan, right?
From Japan.
Oh, Japan.
He was my student, PhD student, and went to Professor Aida. And Takuzo is a tough guy, right? It's much tougher than me, right? So he went through there. I think every young guy, if you want to be successful, you have to go through tough life. If you don't go through tough life, you'll never be successful. Then people say, how about you? I tell you, I was in Heilongjiang province in Heihe as a farmer for 5 years. Could you go with me? Okay, that is a really tough life, I tell you. Okay, so it's everybody have to have a tough life, right? Then you can be succeed. So this is the way which I think when he joined us, our university is very generous with a salary of how much each year?
Each year. Per month?
No, yeah, per month.
Okay.
Yeah, this is about 800,000 yuan
Okay.
per year, right?
Okay.
With 4 million startups. Dongsen would like? You can
The double.
you can
Oh, perfect.
use triple
Okay.
if you like.
Okay.
You think about in Japan.
USD.
In Akron. Akron is older story. It's not now, yeah. I think 800,000 yuan each year.
70 to 80,000, 70,000 each month.
Per month, right?
Oh.
So he bought a very fancy car. His car is better than my car.
Okay, good. Okay, I think only being tough, at the same time being soft,
Yeah.
can we become giant? Okay, with that, we thank Professor Stephen once more time for his wonderful, very exciting talk. Thank you very much.
Thank you. Thank you very much for your invitation.
Okay, we have lady.
Oh,
Okay, and to express our appreciation to your lecture, Pierre made this special plaque for you with your name and the title of the lecture.
thank you. Thank you very much. Thank you. Okay, thank you. Go ahead.
I also wanted to invite Professor Wang, Professor Liu, Professor Su, and Professor Xing come to the stage to take a photo together.
Oh. Thank you. Thank you. Thank you very much.
Yeah, thank you very much. Yeah, I also wanted to thank everyone for attending today's lecture, and especially for those who ask questions that make this lecture even more meaningful. So Professor Cheng will be around, and if you wanted to talk to him a little bit after this lecture, you are more than welcome. Then this lecture is adjourned. Thank you very much.